Hey guys, welcome back to another video. In this video, we're going to look at energy graphs against the time. In the previous videos, we looked at energy being plotted against position. But in this video, we're going to focus on energy, be it kinetic energy or the potential energy being plotted against time. So for that, we need the help of the velocity curve. What is the velocity curve? The equation for velocity is, it's given. So the equation for velocity is v naught, the maximum velocity, times cos omega t. Therefore, you know the graph or the curve for velocity is basically a cosine curve. It is a cosine curve. Therefore, if you break the v naught, you're going to get a omega, which is the amplitude. A omega is the amplitude or the maximum displacement. The maximum velocity. So over here, the amplitude is a omega, the maximum velocity. Okay, if you know that, now if we want to draw or plot the kinetic energy curve, we need the help of velocity at any given time. So we know this is the curve for velocity. So if we want to plot the kinetic energy curve, this is already given over here for both kinetic energy and potential energy, but we're going to do it again from scratch. So it's going to look like something like this. If I put everything down and do it again. All right. So if we want to plot the kinetic energy, Ke, against time, how are we going to do that? So let's plot these as position 0, 1, 2, 3, 4. If we know the kinetic energy at 4 of these positions, that's going to be more than enough to plot the other ones. Great. So at position 0, what's happening is the velocity is maximum. Half mv square is basically your kinetic energy. If the velocity is maximum, v is v max, in that case, kinetic energy is also going to be maximum Ke. In that case, what's going to happen is you're going to get a maximum kinetic energy value at position 0. So you're getting a maximum kinetic energy value, which is actually half m omega square a square, if you remember from the previous video, or you can derive it from here as well, as the amplitude is a omega, and the equation for kinetic energy is half mv square. Plug in a omega and you get half m a omega whole square. So it's basically the same no matter whichever equation you use, the one that is with respect to time or the one that is with respect to position. You're going to get the same value. All right, so if you know that, you know the maximum kinetic energy is half m omega square x naught square or amplitude square. Great. So at position 0, the kinetic energy is maximum. And at position 1, you know the velocity is 0. The velocity is 0. So what happens over here is for 0 as the velocity, the kinetic energy is also going to be 0. Since half mv square is the equation for kinetic energy, when velocity is 0, the entire expression becomes 0. In that case, the velocity is going to be 0. The kinetic energy is going to be 0. For position 2, again, notice that it is maximum velocity in the opposite direction or in the negative direction. What's going to happen over here is just plug in minus a omega into the equation for half m v square, which is the equation for kinetic energy. If you plug in only a omega minus a omega, you're going to notice that the entire equation becomes half m a omega whole square. Why? Because the minus is going to turn into plus because it is squared. So the value you get is exactly the same as previous. So in this case, when the velocity is maximum in the opposite direction, even in that case, the kinetic energy is going to be maximum, since there is no positive and negative when it comes to energy. Great. So the kinetic energy is maximum. Again, at position 4, what's going to happen is, since I skipped position 3. Right, at position 3, what's going to happen is velocity is 0. Position 3, velocity is 0. In that case, what's going to happen is kinetic energy is in return going to be 0 as well. So plot 0 over here. Again, at position 4, what's going to happen is velocity is maximum. So kinetic energy is maximum as well. So if you plot it, it's going to look something like this. Now, if you're good at trigonometry, you should already understand that this is actually a curve that is synonymous to a cos square curve. This is the curve that you get when you plot cos square x. Right. So how do we know that? Basically, you can see that within the period of one cos x, or the period for one cos function, you can see that you're getting two periods over here. For the period of 1 over here, you're getting two different individual curves. Right. So this is actually the feature of cos square x, or in this case, t. Cos square t, if you look up on the internet, is basically something like this, where within the period of one cos x, within the period for one cos x graph or curve, you're going to get two individual curves or two individual periods for a cos square curve. So that is a unique attribute for cos square curves. And how we get cos square for kinetic energy, I'm going to show that as well. So for now, you understand and know that the kinetic energy is going to look like this. This is the shape of kinetic energy against time. Right. So if you know that, we can move on to potential energy. So for potential energy, it's basically the opposite, where the kinetic energy is maximum, potential energy is supposed to be 0. Potential energy is 0. At position 0, the potential energy is 0. Why? Velocity is max, meaning, where is it? For, let's say, the same Bob experiment, here V is max, but there is no change in height. In that case, PE is 0. So we are plotting 0 over here. Again, at position 1, notice that kinetic energy is 0. In that case, it is at a position like this. In this case, the maximum height is received, and the potential energy is again maximum. So for that, we're going to get a maximum value. If you repeat it for other points, this is how the plot looks like, and the curve that you get is going to look like this. So if I erase the kinetic energy curve, this is your potential energy curve. Great. So if this is your potential energy curve, you know that there is a trigonometric function for this as well. So basically, if you're good at trigonometry, you already know this is synonymous to a sine square curve. Right. So the curve for kinetic energy is basically a cos square curve, and for potential energy, it is a sine square curve. Right. How are we getting those? We're going to look at it in a minute. Right. This is the curve for both of them, and the red line is basically the total energy, which is constant throughout. If you add kinetic energy over here and potential energy over here, you're going to get this. You're going to get half ma squared omega squared. So add the potential energy and kinetic energy at any given time, and you're going to get the total energy, which is always constant. Great. So how are we getting the equations? You don't need the equation, but I'm still going to show it. For kinetic energy, the graph equation is derived as, the equation for kinetic energy is half mv squared. So plug in the equation for velocity, which is a omega or v naught cos omega t whole square. Now, what happens is, after you square the values, a omega becomes squared a omega. So a squared times omega squared. Now, if you square cos omega t, it becomes cos square omega t. So this is how you're getting a cos square variable in your equation. Right. This is the reason your graph looks like this. Sorry for the bad cos square curve, but you get the point. The pink curve is the kinetic energy curve. Right, so this is how we're getting a cos square curve. Okay, now by the way, you know that all of this is a constant. None of this changes. The amplitude is always the amplitude. The maximum displacement, that doesn't change. The omega, angular frequency, stays the same, never changes, and mass never changes, and half is just a constant. So if you know all of these are a constant, you know the only variable in this equation is cos square omega t, or to be specific, the time. So where is cos square omega t maximum? Or what is the maximum value for cos square omega t? If you're good at trigonometry, the cos square function lies between 0 and 1. Why? So the cos function lies between -1 and 1. So cos square, if you square either side, becomes 1 and 1. So you know this is not true, because there is actually a minimum, another minimum value, which is basically 0. You know, the function does go to a point where the value is 0. Therefore, the least value is actually 0 for cos square, not -1, since if you square -1, the value you get is 1. Therefore, the least value is not 1, it's going to be 0. So the cos square varies between 0 and -1. If you want to see it on a graph, this is basically a cos graph. Now, if you take the square of all of the values, you're going to get this value, which is, let's say, -1. This, let's say, is +1. This -1 gets over here. Okay, so this is how we get the cos square curve. When you square this value, you get a +1 value. When you square this value, the value you get is over here. When you square this value, you get a value that is over here. When you square this value, you get a value that is over here. Right. So basically what's happening is the negative values get squared and become a positive value, which is why the cos square curve lies between 0 and +1. Great. So now we know how we're getting a cos square shape for our kinetic energy curve. Now, if we go back to potential energy, oh, by the way, for kinetic energy, the maximum value is, if you want to prove with this equation, you know the maximum value for cos square is 1. So the maximum value for kinetic energy is half ma square omega squared times 1, or half ma square omega square. So again, you can prove that this is indeed the maximum kinetic energy. Right. So for this part, what's happening with the potential energy? What's happening with the potential energy is basically, you know, the total energy, which is half ma square omega square. You know the kinetic energy, which is this, and you know, or I mean, you don't know potential energy. Right. So if you make potential energy the subject, you get half ma square omega square, half ma square omega square minus this, and if you take half ma omega square a square, common from each of these expressions, you get 1 minus cos square omega t. This, if you go to trigonometry, is actually sine square omega t. So this is how you get a sine square curve for your potential energy curve. For your potential energy curve. Right. So if you want to do it with the curve, with a sine curve, you know, the sine curve looks something like this. And if you take the square of this becomes this. And basically, it turns into something like this. So all the negative values get squared and become a positive value, and all the positive values, let's say 1 or 2, get squared and gives you a bigger value.